Modern physics has a massive unresolved question. Why does the universe seem to favor matter over antimatter? To find the answer, researchers are hunting for microscopic differences in how these identical but oppositely charged twins behave. The primary tool for this search is a technique called laser spectroscopy. Physicists tickle an atom with a laser beam and measure the exact wavelength or color of the light it emits in response. In a perfect scenario, every identical atom would shine with the exact same pristine hue. These sharp, predictable signatures allow scientists to calculate the natural constants of the universe with extreme precision. But real life is chaotic. Atoms don't sit still. They careen around and constantly smash into their neighbors. This chart shows exactly what happens during those collisions. The constant jostling deforms the atom's electrons. The crisp, intrinsic color collapses and smears outward into a blurry, rainbow-like spread, a problem known as spectral broadening. To get clear readings without that blurring effect, physicists are usually forced to test these atoms in highly isolated, extremely low-pressure gases, simply to keep them from crashing into each other. In 2013, a researcher named Anna Soter proposed an experiment at CERN that went completely against this standard practice. She wanted to fire hybrid matter-antimatter atoms directly into a dense bath of liquid helium. To see how the atoms would react, the team steadily chilled this liquid helium to near absolute zero, specifically dropping the temperature below 2.2 kelvins. Based on standard physics, immersing atoms in a dense liquid should subject them to relentless battering. The spectral smear was expected to widen perhaps 1,000,000 times over compared to the readings in a thin gas. But this graph shows a direct comparison between those predictions and the actual data. Instead of generating a massively wide, shallow curve, the reading did the exact opposite, producing an impossibly tight, razor-sharp spike. Despite being suspended in a dense, freezing fluid, these hybrid matter-antimatter atoms were somehow acting in perfect, undisturbed unison. When you look at the immense scale and intricate engineering of the particle detectors used to monitor these tiny interactions, it highlights how bizarre a pristine reading like this really is. Generating a perfectly sharp signal inside a chaotic liquid seemed so mathematically improbable that the researchers sought on their own data for years, assuming their experiment was simply broken. To figure out what actually happened, we have to start by zooming out to the environment outside the atom. Specifically, what happens to the helium bath at exactly 2.2 kelvins? Crossing that cold threshold forces the liquid helium into a bizarre quantum state known as a superfluid. In this state, individual atoms lose their separate identities and flow together in a unified wave, moving entirely without internal friction. Because the fluid is frictionless, it effectively takes the edge off atomic collisions. What would normally be a violent, deforming impact turns into an incredibly mild bump. A frictionless fluid certainly softens the blows, but theoretical physicists calculated it still wasn't enough to generate such a razor-sharp laser reading. The true cause had to be hiding inside the atom itself. That brings the investigation down to the microarchitecture of Soter's specific creation, antiprotonic helium. A normal helium atom has two fast electrons. In this hybrid, one is swapped for a massive antiproton. Its heady weight forces the antiproton to tuck its orbit tight against the core, while the remaining electron's wide path forms a thick protective barrier. Now we can see what happens when the frictionless superfluid bumps against the specific Frankenstein atom. When the soft superfluid bumps the atom, it only grazes that outer electron force field. Tucked safely inside, the sensitive, tightly bound antiproton is left completely untouched, allowing physicists to measure its precise color without interference. By solving the mystery of the sharp signal, the researchers provided a way to bypass a long-standing constraint in laboratory measurements. Researchers no longer have to rely exclusively on chasing frantic, zooning atoms through low-pressure gases to get accurate measurements. Placing particles in a bath of superfluid helium acts as an ultra-cold magnifying glass, holding exotic atoms perfectly still without wrecking their delicate spectral lines. The scientific community is already using this technique to fabricate and trap entirely new, short-lived exotic particles, like pions and kaons, holding them stable enough to be studied for the very first time. When you look at the dense tangle of sensors and intense engineering required to operate these massive detection arrays, you realize the power of finally having a clear, stable target to aim them at. By chasing down the mathematical impossibilities of a seemingly failed experiment, researchers discovered a new way to precisely measure the universe's most elusive building blocks.